Hello, this is Professor Keen. Today what we're going to do is talk about A Student's Guide, Volume 2, Chapter 25. And this is really, we're shifting gears here. This is the beginning of Book 3 of Newton's Principia. We've been looking primarily at Book 1. And in Book 3, he begins with a scholium. Remember, his scholia are basically him kind of sitting back and talking more broadly about the implications of what he's been talking about up until this point. So far, if you'll recall, what Newton has done is he's presented his laws of motion, and this was in a very mathematical format. And he illustrated the use of these laws using examples from the motion of bodies in Book 1. That's what we spent our time talking about. In Book 2, which we skipped over, he spends quite a bit of time talking about the application of his laws in understanding light and sound. Where we left off is we had just done some pretty mathematical heavy lifting in Chapter 24 and trying to understand how his laws of motion can be used to understand centripetal forces. Now what he's going to do in Book 3 is he's going to turn these laws of motion around and try to understand what he calls the system of the world. What do we mean by the system of the world? Well, he basically means our solar system. So the word world, basically, it's synonymous with what we would call the universe. So he's going to try to understand the universe as a whole. And the prevalent idea at the time was that the universe had as its center the sun, and the planets, the Earth being one of the planets, go around the sun, and that was the world that people were aware of. So he's going to be talking about the system of the world and specifically trying to use his mathematical laws to understand it. He's going to be developing his law of gravitation. Now, as Newton mentions at the outset of Book 3, you don't really need to read all of Book 1 and Book 2 in order to move on to Book 3. In fact, he says only the people who really care about mathematics are going to be able to slog through all of his other work. He says, so if you're looking to kind of tailor your efforts, it's enough to focus on his definitions and his axioms, or laws of motion, and the first 3 sections of Book 1, which is precisely what we've done so far in studying Newton's Principia. We looked first at his definitions 1 through 8, and then his axioms, or his 3 laws of motion, and then some selections from the first 3 sections of Book 1. Now, as I said, in Book 3, he's going to be talking about his system of the world, or his understanding of the solar system. But before he gets into that, in this scholium at the outset of Book 3, he considers more broadly how we should even be constructing laws of nature more generally, or how should we even be reasoning about nature. And I'd just like to point out that it's really uncommon for scientists today to not merely present their scientific theory, but to also present explicitly their ideas on how science should be done. And yet this is precisely what Newton does. You know, when I pick up a copy of Physical Review Letters, the papers don't start out by explaining how they're going to be approaching science. They just kind of jump into the data and the data analysis. But this is precisely what Newton does. He begins by presenting what are called his 4 rules of reasoning. And it's also interesting to note that he puts these on a par with his axioms, or what we now call his laws of motion. So he has 3 laws of motion, and he also has 4 rules of reasoning. And just as he's going to invoke his laws of motion, or his 3 axioms, in order to justify his universal law of gravitation, so too he's going to explicitly invoke his 4 rules of reasoning in justifying his universal law of gravitation. So just like if you were, for instance, to reject one of Newton's laws of motion, one should reject his universal law of gravitation. So too, he sees it, if you reject one of his rules of reasoning, you must reject his universal law of gravitation. So let's spend a few minutes talking about these universal laws of gravitation. And so what I'm going to do is I'm going to turn off my webcam and show the rules of reasoning on the screen. Okay, so here they are. Here are his 4 rules of reasoning, and I want to make a few comments about each one. So I'll read it first, then I'll make a few comments. So rule number 1, he says, we are to admit no more causes of natural things than such as are both true and sufficient to explain their appearances. So this law, or this rule, is sometimes nowadays called the principle of parsimony. And you might have actually heard of it as Occam's razor. So it was popularized by William of Occam, who lived in the late 13th, early 14th century. And the basic idea here is that when one is trying to understand nature, or come up with a theory for understanding nature, and you have multiple theories that might or purportedly explain this phenomenon you're trying to look at, one should adopt the simplest possible explanation. This is called Occam's razor because you kind of figuratively cut out the unnecessarily complicated theories and use the simplest possible theory. Okay. Now, one of the things that's interesting about this is that this principle is not something that William of Occam came up with or Newton came up with. Claudius Ptolemy, for those of you who might have taken my Physics 101 class where we study ancient astronomy and medieval and modern astronomy, we read Claudius Ptolemy, who was probably the most famous astronomer I guess he was in the 2nd century he wrote, but his books were used up through the 16th century. And Claudius Ptolemy, when justifying his geocentric worldview, that is the view that the Earth is at the center of the universe, he also appealed to what we would now call Occam's razor. He saw his explanation as being the simplest possible explanation. And of course, it wasn't the only explanation available. He was arguing against some people who thought that the Earth was a planet moving around. And he said, no, the simpler explanation is that the Earth is sitting still at the center of the universe. And he argued based on this kind of principle. So I think that's an interesting thing to point out. It's not like Newton or William of Ockham had a monopoly on this kind of idea. Now, another comment that I'd like to make about Rule 1 is it says that we are to admit no more causes of natural things than are both true and sufficient to explain their appearances. And so we need to have causes that are true and sufficient to explain their appearances, but this raises the question of what does it mean to explain something? What counts as an explanation? And you might think back to when we were discussing Aristotle and Aristotelian thinking, and Aristotle thought that in order to explain something, you must answer 4 questions. That is the 4 causes. So the first question is, what is this thing that I'm trying to explain? That would be the formal cause. Also, what is it made of? That would be the material cause. How or who or what made this and how did they make it? That would be the efficient cause. And what is the purpose or goal or end of this thing? And that would be the final cause. And so if you really wanted to explain the appearance of something, one, according to Aristotle, the 3rd century BC thinker, one had to answer these 4 questions. And it's not clear at this point what Newton would count as an explanation, but it's certainly true that by this point, Descartes had already been around and he was already criticizing the Aristotelian criteria for explanation. Things like formal causes were being rejected, and final causes would be eventually rejected. And to the point where today many scientists think that an explanation is really synonymous with identifying strictly the material cause, that is what something is made of, and perhaps the efficient cause, who or what made it. And even in some cases, that is not necessary for an explanation. So at the very least, I'd like to point out that over time, the notion of what counts as an explanation has become more and more lax. Okay, so there you have it, Rule 1 and a few notes about Rule 1. Now, let's move on to Rule 2. Newton's Rule 2, he says, therefore, to the same natural effects, we must, as far as possible, assign the same causes. What does he mean by this? Well, he gives a few examples in the text right after this to explain what he means. So he says, for example, if you want to understand respiration, and you notice that people, man, breathes, and also that beasts, elephants and things, breathe, then probably because they have the same effect, breathing, we should assign the same cause. Namely, they both have lungs, for example. That would be an explanation. So insofar as possible, we must assign the same causes to the same effects. And he uses other examples. For example, if you notice that you drop a stone and it descends when you are in Europe, and you drop a stone and you notice that it descends in America, the descent, because it's the same effect, one should assign the same cause. That is, the stone has weight or gravity in both Europe and America. Likewise, another example, he says, the light of fire in your backyard, for example, and the light of the sun, those should be assigned the same cause, that is, burning of something. And another example, he says, the reflection of light on the earth, for instance, from a mirror, and the reflection of light from planets, for example, when the sunlight shines, reflects off of Venus and makes it look bright in the evening sky. So the laws of reflection are the same on Earth as they are on planets. And so what this rule, by adhering to this rule, Newton is going to be able to say, if we see the same sorts of things, we should assign the same sorts of causes to them, which is a sensible thing to do. Of course, this doesn't always work. There's a problem with this, because if you look carefully at each of these examples he gives, to some extent, they have the same cause, but if you look at it carefully enough, they do not have the same cause. So for example, whereas a man might have a particular kind of lung, a beast might have a different kind of lung, and in fact, fishes might breathe in a different way entirely. Examples of burning. So a fire you burn in your backyard with wood is a very different kind of burning than the burning of the sun, for example, that takes place using fusion of hydrogen of hydrogen into helium, for example. So, and I guess he gives himself some wiggle room here, because he says to the same natural effects, we must, as far as possible, assign the same causes, which I guess that makes sense. So he's giving himself some wiggle room. But the philosophy here is that one should assign the same effects, causes to the same effects. Okay, Rule 2. What about Rule 3? This one is a little bit longer. He mentions, and I'll explain the terms here. I'll first read it and then explain the terms. He says, the qualities of bodies, which admit neither intension nor remission of degrees, and which are found to belong to all bodies within the reach of our experiments, are to be esteemed the universal qualities of all bodies whatsoever. So in order to understand this, let's make sure we understand the specific words he's using. So let's first of all look at, he's talking about the qualities of bodies. This is as opposed, so we have qualities of bodies as opposed to quantities. Okay, so that's a distinction that is being made here. And he says qualities of bodies, and you might think about this as being a parenthetical comment. The qualities of bodies which admit neither intension or remission. That is, they don't increase and they don't decrease in degree. Okay, so what does he mean by this as opposed to a quantity? So remember a quantity, maybe this will help explaining this by way of contrast. So a quantity is something that can increase or decrease numerically. So for example, he had talked, you remember in his definitions, about quantity of motion or momentum. So something might be going at a certain speed that you can assign a number to. And in fact, he assigns a number to quantity of motion when he considers collisions. So the specific value of the momentum of an object can increase or decrease. It can become intensified or lessened. Okay, so a quantity can go up or down. Another example would be quantity of matter or mass. The quantity of matter in an object, you can have more or less quantity of matter by taking a ball of dough and adding more dough to it. You've increased the quantity of matter, you've increased its mass. On the other hand, qualities themselves, he said, cannot go either up or down. And if these are things that belong to all bodies that we've experimented on, then those qualities should be seen as universal qualities of all bodies. So if these qualities seem to belong to all bodies that we've done experiments on, then we're going to generalize and say these are in fact universal qualities of all bodies. Okay, so what are some examples he gives of qualities? So I just gave examples of quantities like momentum and mass. What about qualities? Okay, I should probably write this down here, give myself room there. Qualities. Well, they're things that cannot be increased or decreased. So for example, he says extension is an example of a quality. By extension, he means size. So you might think this is what Descartes called res extensa. The fact that objects are extended objects, they have size. So although a ruler could be either 1 meter long or 1 foot long or 1 yard long, the particular length of it might differ. Nonetheless, the very fact that it has extension, it is an extended body, is a quality of all bodies that we're aware of. Every body, in fact, is extended. The extension might be different, but the very fact that it has extension is a quality. So that would be one example of a quality. Another example of a quality would be hardness. He says, while it is true that some bodies are harder than others, the very fact that they have hardness, that they have a hardness, this is a quality that belongs to all bodies that we're aware of. Okay? Another example of a quality would be impenetrability. Impenetrability. You cannot have two objects located in the exact same place at the same time. One must displace another in order to take its place. It is true that if you take, for example, a piece of foam, you can stab it with a knife, and you might say, wait, that foam is penetrable. Well, in a sense it is, but in a sense it isn't. What you're really doing is the knife is pushing aside the foam when it goes into it, and the knife and the foam are not occupying the exact same places at the same time. And what Newton argues is that all bodies are impenetrable. They cannot be in the same place at the same time. Another example of a quality is, he says, movability or mobility. All objects that we are aware of are able to be moved. Some are harder to move, some are easier to be moved, but nonetheless, all objects can be moved. So mobility is a quality of all bodies within the reach of our experiments. And another example, the last example he gives, it might not be the only further example, but it's the last one that he gives, is all bodies have inertia. That is, when they're in motion, they tend to stay in motion. At rest, they tend to stay at rest. This is really a consequence of the fact that they have mass. So they're hard to change their state. Okay, now he says that the very fact that all objects that we see, all bodies we see, seem to have these qualities, we should generalize this and say they are universal qualities of all bodies whatsoever. Okay, so he goes on to say here also that we assume that the unseen parts of bodies too are hard and impenetrable and mobile, and they have inertia. For example, if you have a clump of dough, that might be comprised of very, very tiny pieces of dough all put together. But even though maybe you're not looking at the tiniest piece of dough, we can assume by this generalization we just mentioned that all those little parts of them also have these, at least these 5 general universal qualities. And he says this is the basis of all of his natural philosophy. Now, of course, this raises some interesting questions. This raises the issue of atomism. Okay, so he kind of goes on here and talks and broaches this topic of atomism, even if he doesn't solve it. So he says we really have experience dividing any body we have. We can always seem to be able to divide it. You take a glass of water, you can pour it into 2 smaller glasses of water. This you can pour into 2 even smaller glasses of water, and so on and so on. You can keep dividing things, and you can conceptually divide a body infinitely. That is, they are potentially infinitely divisible. But he says we have not actually divided all bodies infinitely. And he says this is really a question that's open to debate. Whether or not one can potentially divide everything infinitely, that's not open to debate. But whether one can actually divide all bodies infinitely, or whether one comes to a limit to which you can no longer divide something, that is an open question. And he said, so this, the atomists at this time were saying eventually you'll get to fundamental building blocks which you cannot divide anymore. And others who were not atomists said, well, there's no reason in principle why you cannot keep on dividing things. They do not believe that there are fundamental building blocks. And I think this is still open to debate. But the main point is that, and this is where he's going with his rule 3, is that if we find certain qualities that are inherent in all bodies, these are going to be universal qualities of all bodies whatsoever. And where he's aiming here is he's going to say that if we find, for example, that all bodies around us, like rocks and mountains and apples and so on, seem to gravitate toward the Earth, and if the moon gravitates toward the Earth, and if the sun gravitates toward the moon, and if the planets gravitate toward one another, and if comets gravitate toward the sun, then those are all bodies that seem to exhibit the quality of gravitational attraction, and we can conclude then that all bodies have a principle of mutual gravitation. So he's kind of teeing up here in order to come up with his universal law of gravitation. He's going to set up the fact that things gravitate as a universal quality of all bodies, a principle of mutual gravitation. Okay, let's go on and talk about Rule 4 briefly, and then we'll be done. So Rule 4, I'll read it first, and then I'll make some comments. So Rule 4, he says, in experimental philosophy, we are to look upon propositions collected by general induction from phenomena as accurately or very nearly true, notwithstanding any contrary hypotheses that may be imagined, till such a time as other phenomena occur by which they may either be made more accurate or liable to exceptions. Now, this is kind of wordy, but it's actually a fairly simple principle if we take it apart and look at it carefully. This is the principle of induction. What do we mean by the principle of inductions? He says in experimental philosophy, we're to look upon propositions collected by general induction, induction from phenomena. What is induction? Well, let me do it. Let me explain this by way of contrast. So induction is forming a general law from particular cases. Okay, from particular cases. So for example, let's suppose that I'm sitting here in my library. I've used this example before, but I'll use it again. And I look out the window and I see a red bird sitting on a branch outside of my window. And I look out the window a moment later and I see another red bird sitting on a branch outside of my window. And I look outside a few minutes later and perhaps the next week, and I continually see red birds landing on the branch outside of my window. I might come up with Dr. Keene's law that all birds are red. That would be forming a general law from particular experimental observations. And what he's saying in this rule is that this principle of induction, we should assume that it is accurately or very nearly true, even if someone could hypothesize or imagine that the law could be broken. So, for example, someone might come to me and say, yes, Dr. Keene, I know that you have this all birds are red rule, but in principle, we could imagine there are blue birds. And what Newton here is saying, well, just because you can imagine it, just because it is logically possible, doesn't mean one should disregard the law that all birds are red. Now, of course, if I then go and look out the window and I see a black bird or a blue bird, then that would invalidate my law that I arrived at from induction. And then I would have to revise it, and that's what he says, till such time as other phenomena occur by which they may be either made more accurate or liable to exceptions. So that is what we mean by the principle of induction, and what Newton here is saying is that he is going to adhere to this principle of induction. This is contrasted from the principle of deduction, or deductive reasoning, which is really deriving consequences from axioms. So this is more like what one does in a geometry class. So you start out with an axiom, for example, that if you draw parallel lines, they will never cross. And then you, from that basic axiom, that starting point, one comes up with propositions that follow logically from those axioms. Another axiom might, for example, be that nothing changes without a cause. So this was an Aristotelian axiom. If you have anything in nature, it does not change unless there's a cause of change. And in fact, this is one of the axioms that was adopted then by Newton. It becomes, in a more specific mathematical form, his first law of motion. He says that objects in a state of motion do not change their state of motion without a cause. So here Newton, whereas Aristotle was saying nothing changes without a cause, you might think about nothing gets hotter or colder or sicker or healthier without a cause. Newton is specifically constraining his considerations to object in motion. So objects that are in a state of motion from one place to another do not change their state of motion without a cause, and that cause in Newton's case would be a force. So Newton states that as an axiom, and then because this is his mathematical principles of natural philosophy, he then goes on to see what can be derived as a consequence of accepting this axiom, and this is precisely what he does in coming up with his propositions and theorems and so on. Okay. I think probably I will stop there, and in the next lecture I will jump into book 3. We'll be talking about his phenomena, and that is his general observation. He's collecting the observations about the solar system that are going to then inform his universal law of gravitation.